In this video, we're going to do another problem where we apply the conservation of energy in our engineering formulation to solve a particular problem. Here we're given a pump turbine system with two reservoirs, one at 150 feet elevation and one at 25 foot elevation of the free surface. And we're told that it draws water during the day from the upper reservoir to the lower reservoir in order to produce power for the city of Athens. And then at night, it pumps the water back up so that the water is still available for the next day. And we're told that for the design flow rate of 33 feet cubed per second in either direction, the head loss is 17 feet. And we're asked to estimate the power in horsepower extracted by the turbine during the day and delivered by the pump at night. And the first thing we think of is, well, it's probably going to be the same, right? You're pumping water from elevations that are the same, just back and forth. But that's not really the way it works out due to where the head loss term falls in our energy equation relative to the turbine head term and the pump head term. So let's just go through it and you'll see how that falls out. So the first thing we want to do, as we do with all our problems, is write out the energy equation, conservation of energy equation, its full form. So we'll start with part A, which is the turbine. And like before, we also need to label our points. So we want to get our endpoints right. So we're going to say 1 is the free surface here, and 2 is the free surface here. And again, that's really picking that because those are the numbers we're given. We don't really know what the situation is other than that, but if we work from those points, we have known values. All right, so let's write out our conservation of energy equation. We have Q dot over M dot G plus U1 over G plus P1 over gamma plus V1 bar squared over 2G. And in this case, since we're not given any information about alpha, we can assume it's 1 plus Z1 plus HP is equal to P2 over gamma plus V2 bar squared over 2G, again assuming alpha is 1, plus Z2 plus H sub T plus H sub L plus U2 over G. Okay, so there's our full form of the equation for the conservation of energy. And then, just like before, now we're going to look at each term and figure out whether or not it's important. All right, so first term. We're told that there's nothing about heat transfer, so we can assume it's negligible, so this is term 0. Second term, we're not told anything about the temperature changing in the system, so we can assume that U1 equals U2. So here we say U1 equals to U2. And we can do the same thing on the other side. So we go over here, we cross this out and say U1 equals U2. Pressure, well, the pressure at 1 is a free surface. It's at atmospheric pressure, which is 0 gauge. So this is 0, P gauge is 0. Just like in the previous video, when we move to the velocity, if we work from that free surface, we assume the reservoir is large relative to the 33 feet cubed per second going through the pipe, then the velocity at 1 is going to be 0. So this term goes to 0, so V is 1 is approximately 0. Z1 we know, so we don't need to worry about that. And then HP, well, in this case there is no pump. We're just looking at the turbine side. Okay. Going down to point 2, the pressure at point 2 is also the free surface. That's a 0 gauge, so this term is 0. We make the assumption again that the reservoir is large relative to the flow rate through the pipe, so this is V is approximately 0 at point 2. We know Z2, we have a turbine, and we know the head losses. All right, so now we can rearrange that and get an expression for the turbine. So we get H sub T is equal to Z1 minus Z2 minus H sub L. Okay, plug those numbers in. We get 150 feet minus 25 feet minus 17 feet. H sub L is equal to 100 feet. Right, so there's our answer, but we're asked to get that in terms of horsepower. So we have to recall our definition of H sub t. So if we say H sub t is equal to Wt dot over m dot g, we can rearrange that and get Wt dot is equal to Q times rho, that's m dot, so this is m dot, right, times g times H sub t. We have all those numbers, so we can plug that in. So we get 33 feet cubed per second times 1.94 slugs per foot cubed times 32.2 feet per second squared times 108 feet. We do the math there and we get W dot T is equal to 2.23 times 10 to the fifth foot-pounds per second. And then we can use that at conversion above where we say that 1 horsepower is equal to 550 pound-foot per second. So we can put that in. So we just divide that our answer by 550 and we get 405 horsepower. All right. So that's our answer for part A, and that's a pretty sizable amount of horsepower. You know, it's a sports car amount of horsepower that this turbine is able to extract to help power the city of Athens. Okay, so now let's move to the second part of the problem. So part B, we're going to do the same thing that we just did, except for now we're going to be looking at the system at night when we're pumping water from the lower reservoir back up to the upper reservoir. So we're going to switch the direction, and instead of relabeling, I'm just going to put the 0.2 on the left-hand side of the equation and 0.1 on the right-hand side of the equation. So that's going to look like this. It's going to be Q dot over m dot g plus U2 over g plus P2 over gamma plus V2 bar squared over 2g plus Z2 plus H sub P is equal to P1 over gamma plus V1 squared over 2g plus Z1 plus H sub T plus H sub L plus U1 over G. Okay. Now we're going to go through again and get rid of the terms as we can. All right, so we're told nothing about heat transfer, so no heat transfer. Told nothing about the temperature changing, so we can assume U1 is equal to U2. So remember, we already assumed that changes in the internal energy are just functions of temperature. Told nothing about that, so we can assume those are equal. Pressure at point 2 is a gauge. This is 0. We assume that the velocity at the surface is small relative to the flow in the pipe, so this is 0. And we do have a pump and we do have Z2. We know those two terms. We're actually solving for HP. All right, P1 at the free surface of the upper reservoir is 0 gauge. The velocity is small relative to the flow in the pump, so this is 0. We know Z1, there is no turbine, and so now we have our equation. We can rearrange that, and we get H sub P is equal to Z1 minus Z2 plus H sub L, and that's equal to 150 feet minus 25 feet plus 17 feet, and H sub P is equal to 142 feet. All right, again, we're asked to get that in horsepower. So from before, we can write WP dot is equal to M dot G H P is is equal to rho Q G H sub P. Plug in our numbers here. We have 1.94 slugs per foot cubed times 33 feet per second feet cubed per second, sorry, times not 32.2 feet per second squared times 142 feet is equal to 2.93 times 10 to the fifth pounds feet per second, and then we do make that conversion, it's 532 horsepower. So there's our answer for part B. And on the surface, this doesn't make a whole lot of sense. It costs more, it takes more power to put the water back up than take the power out on the way down. But what we have to remember is the key difference is the price of electricity. Electricity is very expensive during the day and cheap at night. So if we draw the power out during the day when it's expensive and sell that power and then pump it back out at night when it's cheap, we can actually make this a functional system where we pull power out and put it back in at some cost. All right, so we'll look at another problem in the next video.